Welcome back to another episode of Quaranteaching. Alright, so today, station models. We're going to pick up where we left off yesterday, talking about the atmosphere. We were talking about the variables a couple days before that, temperature, dew point, relative humidity, wind speed, the basic variables of weather. So today, I'm going to introduce to you a tool called a station model. So most of you have probably played video games either on your phones, maybe you played it on Xbox, maybe you played it on PlayStation, you play it on something. You may not know what this is called, but when you're looking at the screen and you have all the information around the border, it's called a heads-up display. And all those things are coded in ways that you don't need full-on sentences and paragraphs to describe what every symbol means, right? So there's lots of symbols with meanings. Our station models are going to be like our heads-up display with your video games, except we're going to be using these in order to help us predict the weather. All right, so a station model, we need to find ourselves on page 13 of the reference tables. We're going to be here. We've got a few places on this page that we're going to be investigating and using today. One of them is going to be down here, which I will highlight later. We'll be using temperature conversion, graduated scale. We're going to be using the pressure graduated scale as well. So let's get going. Now, how to read this thing is going to be interesting, okay? And as we read it, there's going to be different types of conversions we have to do in order to understand exactly what that amount means. So I would like to point out first that we're going to practice converting some air pressures from these codes. So here I've got a section that I've highlighted with a box here with a code that says 196. I want you to know that all the converting and all the rules for converting will be down here. So let's read through this kind of quickly in order for us to see how we need to start converting. So the most important aspect of this is deciphering the pressure on this model. So there's a rule here, and these sort of have to be memorized because the rule with a 9 doesn't exist in this example in your reference tables. Only the example with the 10 in front is represented here in your reference table. So let's read through this. We're going to place a 9 in front of a 3-digit code like this as long as the first digit in that code is the number 5 or higher. Then we're going to put a decimal between the last 2 digits of that code. Okay, our second rule before we practice, place a 10 in front of these digits if the first value of this code is the number 4 or lower. Then we're going to do the same thing by placing a decimal between the last 2 digits of the code. And this will result in us having what the actual air pressure is in millibars. Before that, these codes are not given units. Okay? The codes are purely to help condense the information in the station model so it's not as lengthy. All these words here don't exist on a station model. It looks more like this on the left where we remove all that extra information. So it's a nice and tidy little package of symbols and numbers. All right, so let's take a look at this first chart here to do some practice. The first value in our practice is going to be a code of 233. So the first thing we do is we look and we say, is the first value here on the left, is that 5 or higher or 4 and lower? In this case it's a 2, so it's 4 and lower. So we place a 10 in front. And then the last step of the instructions are we place a decimal in between the last 2 digits. So when we do that, our code converts to a real air pressure of 1023.3 millibars. For our second example, we have 822. That is the code, not the pressure yet. So our first number is an 8. So it abides by the rule here where we're 5 or higher. So we're going to place a 9 in front. And then we're going to do the same process of placing a decimal between both of the 2's at the end. And now we have a complete pressure of 982.2 millibars. Okay? I'd like you to pause for a moment and try out these 3 on your own. Go ahead, pause, give it a shot. Okay, so you've hopefully paused and you're not just constantly watching the video. If this is to convert, we have a 0 in front, so I need a 10 because it's 4 and lower, that rule. I'm going to continue to add all of my values so that at least I know I'm not going to forget any. And then I'm going to place a decimal between the last 2 digits of that pressure and add my units. So the code 012 will convert to 1001.2 millibars. 999 out of 9. So that's not a G, that's the board messing up, but 999, you add a 9 in front. So you should have then 4 9s. Place the decimal in between. You have 999.9 millibars. Last one. Okay, so you get 1022.1 millibars. All right, now I'm going to show you one moving back to the original. I'm going to take this one here, 953.2 millibars. I'm going to use that as my example. So we have 4 digits here. We have to identify whether we have a 9 or a 10 in front. Pretty easy. We have a 9. So we're going to drop the 9 and remove the decimal. So I should have a code of 532. No units. Drop the 9, drop the decimal, get rid of the units. You have your code. So pause the video, give these 2 a shot. Okay, so you've had an opportunity to do these ones, so let's see what they convert to. So I've got 1000.0 millibars. I have a 10 in front, so I'm going to get rid of the 10, get rid of the decimal, get rid of the MB for millibars, and I end up with a code of 000. So notice 000 does not mean you have 0 pressure, right? This last one, we have 972.4 millibars. We're going to eliminate the 9. We're going to eliminate the decimal, and we're going to get rid of the MB. And we have 724. That's the code. Right? So hopefully this gives you at least a nice little introduction into how we're going to either add codes onto station models or convert pressures off the station models for our use in determining weather. Next step, we need to learn how to do some temperature conversions so that we know what we're dealing with here on a day-to-day basis, depending on whether you're in Celsius or you're in Fahrenheit, or you're in millibars of pressure, or you're in inches of mercury. Hg converts is the elemental symbol for mercury. Okay. So in order for us to get a little bit used to the conversion process, let's take a look at our pressures column. So we've got 2 sides to our graduated scale. Very similar to what we did with the altitude of the atmosphere on page 14 of the reference tables. We are now on page 13 of the reference tables. Okay. Now, conversion is all about figuring out what the interval is and what you're counting up by so that you're able to make estimates in between and right on the lines themselves. So let's zoom in even further here so we can determine what the interval is in this scale. So on the left side, we have millibars. We're going to try to figure out how much we're counting up by. So it's a good idea maybe to indicate that we are solving for the interval right now. Okay? Now, we have 1012, 1016. You can pick any 2 you want, but we have 1012, 1016. If we were to solve the difference between them, you have a difference of 4 millibars. If we are to look at how many gaps are in between, we have 1, 2, 3, 4. I think this is going to make it pretty easy. So each line, smaller tick line here, is going to count up by 1.0 millibars. But don't forget that if something falls in between, you're going to have to do some decimal estimating. Okay? So if we have 1016, 1017, halfway is going to need to be approximately 1016.5 millibars. Okay? Now on the opposite side, over here, for our inches of mercury, we're going to do an interval again. I'm going to write a little smaller because we're running out of space. My gap, IN, HG. All right, so we've got decimals we're dealing with here. Doesn't look like our whole number changes all that much. So let's pick a place that's kind of nice to solve this. I like starting here at 30.00. That's going to make it nice and easy to subtract and divide for our interval. So we've got 30.00, and I'm going to use 30.10 inches of mercury to bookend where I'm going to solve my interval. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Looks to me like if we have a 0.10 difference between my two values, and I have 10 gaps, then each of my gaps is going to be worth 0.01 inches of mercury. So that is the interval on the right side. Left side, 1.0 millibars. So the conversion process is simply identifying where you are on either side and estimating the amount for the other side. Let's talk temperature scale. Okay, so we're going to need to figure out intervals here as well. So interval, and this down the center is going to be, you should know, based on the top of the diagram, Celsius. So over here, this is going to be interval in degrees Fahrenheit. Looks to me like we've got a good place to start here for 100 to 120. Looks like we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we've got 20 degrees Fahrenheit difference, 10 spaces. So we're going to end up with a 2 degree Fahrenheit interval. So every line is 2 degrees Fahrenheit. The middle one, Celsius, I think that's going to be straightforward. Take our 50, our 40. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we've got an interval of 1 degree Celsius. And because it's in the center, we're going to go to the top and we're going to write interval here. And I'm going to abbreviate to save some space because there isn't a lot of space in that title. Kelvin, we will talk more about Kelvin later, but Kelvin is very similar to Celsius in its interval. However, the scale goes down to absolute zero, okay, rather than any negative number. So this is an absolute temperature scale. You'll be learning more and using this more in chemistry. All right, let's get to do some of these practice ones now. So I would say with the time you have, pause the video, practice these. I'll review a couple of them, okay? But you should be able to do them. So go ahead, pause the video. Okay, so you had an opportunity to probably pause the video, and I'm set, ready to do a few of them. So we've got our pressure conversions, 972 millibars. We're going to go down to 972, and it looks like it just, honestly, it's close enough to say that 28.7 inches of mercury. Our next one is going to be 1025, so we'll go way up here to 1025, and it looks like we're talking about 30.265. Yeah, I say 0.5 because it falls in between the lines. It falls in between a 0.01. But if you had said 30.26 or 30.27, you will be fine. All right, let's come down here. I'm going to do these two, converting them to millibars. I'm going to leave these two open-ended, okay, in case you didn't actually practice them. So 28.60 millibar or inches of mercury, and we're finding millibars. So it looks to me like it's 1002.5 millibars. 30 on the dot. So 30 on the dot is 1,016.0 millibars. One thing I do want to point out to you all on this scale is that you've been told what 1 atmosphere is worth for our purpose of Earth, and that is 1,013.2 millibars, and if converted, it's 29.92 inches of mercury. So add that as well in case you want to start to memorize these in case you need them later this year. All right, so temperature conversions. We've got 100 degrees Celsius and Fahrenheit. That one, if you remember from phases of water, the phase change for vaporization, 212 degrees Fahrenheit, but if you don't remember it, it is here. Okay. Let's do a negative. So negative 15 to Celsius. So we're going to find negative 15. The closest value is probably going to be negative 26. Negative 26 Celsius, but it's kind of close also to negative 26 is good enough. So negative 26 Celsius. All right, I'll leave these two open-ended for you as well. And I'm not quite ready to do the practice. Now I'd like to walk us through each of these aspects of the reference tables so that we can do some practice. And once we start looking at them in weather maps, we'll have a better idea how to interpret the weather. All right, so let's get rid of that. So again, the idea is this station model is how it's going to appear on your weather map, and each of these areas and symbols indicate something that's happening. So let's just start with what each thing means. So in the center, what we can see is this circle is going to be the amount of cloud cover. So in this case, the area that's shaded in is the amount of cloud cover you have in terms of percentages. This looks about 3/4 full, which is 75% cloud cover. Okay. They can be open, they can be half, they can be full. A full station model, a fully shaded circle, does not necessarily mean it's raining. We've had days where it's been fully cloudy and not raining before. Here, our barometric pressure, which we spent a good deal of time on. But notice that the 196 has been shown over here in full conversion, so if you forget to add a 10 and a decimal and a unit, it's there. You have to remember how the 9 works. That number there has to be 5 or higher. All right, so this is the barometric trend. So is pressure getting higher or getting lower? And is it happening over a 3-hour period? So here we've got a plus 19, so we know that pressure is going up. We also have a slash, a forward slash, indicating an upward slope in an increasing trend. And to convert this, you add 1 decimal and a unit. This is how much this value has increased by over 3 hours. So we know that we're moving into higher pressure. And eventually you'll learn that moving into higher pressure means these clouds start to go away and we have a nice day. Right? Precipitation is the amount of precip over the last 6 hours. That precipitation could be snow, that precipitation could be rain, could be sleet, could be freezing rain, could be a multitude of different precipitations. All right, so wind direction, this little tail here. So we have what are called feathers on our tail, and each feather is 10 knots. Okay? There's a conversion down here. 1 knot equals 1.15 miles per hour. So 10 knots KTS times 1.15, we'll just throw parentheses in here, that maybe that'll be easier. Miles per hour will give you the total number of miles per hour that each knot unit is worth. So if we have 10 knots, you multiply by the conversion factor. In our example here, it's 11.5 miles per hour. So that you have at least some idea that if you're given knots, you multiply by this factor to get miles per hour. Changing my color a little bit here. So also this tail, think of this tail as if it's like a little airplane. Okay, and the airplane's flying to somewhere, some destination. But in order to fly to somewhere, it must have come from someplace. So our tail always points to the direction that the wind came from. Okay? Meaning that this tail is pointing, if we had a north-facing compass like this, the wind is coming from the southwest. So in this picture, the assumption is that north is here. So a whole feather, 10 knots. Half feathers are 5 knots. So the way we state this whole thing is that we have 15 knots from the southwest. The only time that you won't see a feather at the end of the tail is when you're dealing with just and only 5 knots. So for example, I'd like you to put a tail with an indent and label this as 5 knots. This is the only time a feather will not be at the end of the tail. If there's one feather at the end of the tail, it has to be automatically interpreted as 10 knots. Dew point in Fahrenheit, not Celsius like on page 12. So we did a lot in Celsius to begin with, and now we're doing this little flippity flop between units, which can be a little confusing. I understand, but this, on our station models in the United States, we're using Fahrenheit. Visibility in miles. How far away can you see during the day? Are you being blocked due to the precipitation or the humidity effects, or maybe you have something like fog? So visibility, amount of miles you can see without being blocked. Then you have present weather. Present weather in this case is snow. And how do I know that? Because we have all the present weather symbols down here. One thing that they do leave off in this, and they do occasionally use, is that there may occasionally be dots above your thunderstorm, meaning it's like a downpour. I mean, like, it is just flash flood type event. All right, but we've got drizzle, rain, small, not precip, hail, thunderstorms, rain showers, snow, sleet, freezing rain, fog, haze, not precip, and then snow showers. Okay? So showers mean we've probably got a lot more snow coming down than just a little bit of snow. Okay? Each of these can be present within that weather symbol space over there. Then we have temperature. Temperature is 28 degrees Fahrenheit. So if we go back to looking at dew point, relative humidity, and we start to think to ourselves, look at these temperature differences. We've got 28 degrees Fahrenheit, 27 degrees Fahrenheit. It's really likely that either it's about to rain again, or it did just start to rain, because it looks like we do have some clouds that may have resulted in some rain, and we're being told that in the past 6 hours there's been precipitation. But wait, rain? No, not rain, snow. We've got a symbol for snow, and the temperatures are below freezing. So this gives you a nice beginning understanding of how to use station models. So let's go back to our practice. I'd like you to take this information off and place it onto the data to the left. Over here, I'd like you to take the data and put it onto the station model. So if you haven't done so, go ahead and pause the video and give these a shot, and then we'll start to go over some of it. Okay, so you've had an opportunity to go through it, I hope, on your own, and we're going to start to pull the information off our station model, give it the units, do the conversions, and place it here. If there isn't anything present on the station model, you leave it blank over here in the recorded area. So temperature, 25 degrees Fahrenheit. Dew point, 24 degrees Fahrenheit. Wind speed, 15 knots. Wind direction. We are going to have to assume everything that direction is north. So this is coming from the northwest. The weather, we've got weather, snow. The pressure, we got 996, so we put a 9 in front. So the conversion will be 996.6 millibars. Cloud cover, 100 And we have a precipitation on the last 6 hours of 0.25 inches. Okay. Over here, we've got to put it onto the station model. No units. No units. 65 for temperature, 56 for dew point. We want to get our tail on here first, so it's south, and 1 feather for 10 knots. We've got no weather present, so nothing goes there. We got to drop this 10, get rid of the decimal, get rid of the unit. We have a code of 256. Cloud cover, 50%. Visibility, 3 miles. There's your station model with the data that was present on that day. I'm going to leave these ones open-ended in case you haven't done them and you need an access point. Go ahead and do them now. I think you'll be able to do them. Okay. So pause if you haven't, again, and then try to redo it. If you need the answer to these, please let me know. I'll provide you some more answers to those, but I think it's pretty straightforward now that we have 2 examples. If you've unpaused, we're now moving into the station models guided and independent practice, which you can find within your weather folder on Google folder, or Google Drive with the share folder. Okay? And I'd like you to try to answer these 2 questions on your own. If you need the access points, you have access points here for your station models. And you also have your reference tables. So pause, give those a shot, we'll come back and answer those. Okay, so hopefully you've unpaused and now we're back to go over these ones. So we've got the station model below represents the weather conditions for a location in New York State. So we've got 28 degrees Fahrenheit, we've got 2 mile visibility, 25 degrees Fahrenheit dew point, 100% cloud cover. We've got 15 knots from the southeast. We've got increasing pressure by 0.2 millibars. And we've got a total pressure of 1,000.2 millibars. So the barometric trend for the past 3 hours at this location indicates a steady increase of, well, you got to convert this. So based on the reference tables, it shows us when we get this 2-digit, we add a decimal, add a unit, and we have a plus. So in this case, it's going to be plus 0.2 millibars. All right, so we've got our best option is choice 1. There we go. All right, choice 2. Kids, you have no idea how it's been, but I'm sure it's been just as rough for you. Hang in there. All right, this is probably at least, this could be maybe like day 10 by now. I don't really know. I recorded everything. As you can tell, my outfits don't change that much. All right, so, and I don't even know if you got this far in the video. Give me a thumbs up if you got this far in the video so I know you're actually watching. All right, so number 2, a weather station model is shown below. Ta-da! All right, which information shown on the station model is most closely associated with the measurements from an anemometer? I may have not put that one in an access point, but you know what? I'll give it to you now. Did I? I did! I gave it to you in the access point. Go me. All right, let's go back here. So an anemometer, as my access point tells you, is that we're measuring wind speed with an anemometer. Well, then we have to figure out which portion of the station model is for wind speed. And we're going to go with choice 4. So if you've had an opportunity to do this, you feel comfortable, if you have questions, feel free to throw them down in the comments. I'll try to get back to you as soon as I can. I think I have fixed the comments post 10 days ago because now I'm talking to you maybe 10 days from now I'm shooting it. Anyways, leave a comment if you have questions. Try out the independent practice. Check your answer key. We'll look back at this maybe if we need to get a WebEx session together. Otherwise, I'll catch you in like literally a minute or 2 for the next video, but probably a couple days. All right, bye.